Can you see my screen?
Yeah.
Okay. Let's start with task 4, non-negative matrix vectorization. And we need to talk about...
Can you just give me a recap? Do you have a recap of the previous tasks so that I don't lose track of everything? Oh, yeah. Exactly. Yeah, give me a little bit. Yeah, go ahead. Give me a little bit of a recap. Yeah.
So I need to present it all.
Just quickly, right? Just give me a recap, otherwise I lose track of everything. Yeah.
So I can continue.
No, give me a quick recap of the previous tasks so that
Go
then I understand how we go. Yeah,
one
just quickly. Yeah, just quickly.
Can someone help me
Does somebody
go
else
through
what?
the previous part?
Yeah, you can just show the previous slide, and I'll just go through it.
Yeah, exactly. Okay,
Yeah,
then
so,
just give me a recap. Yeah, give me a recap.
Yeah, then there's there's the test one part that we show that we give it eigen values.
So this is
Lambda
already
to
on
that.
this is on the vectorized images, right? So this is the IBM thesis, right?
We give it a lambda, so it's like the eigenvalue will be slightly above 0. Yeah.
Correct.
Yeah, I think that's it. Yeah, this is that we told last week. Yeah, if we have a YR and or the the lambda value goes higher, we'll have a stronger prior, so that our training will be like fitting the prior we give, but not for the training data. Yeah. Okay.
Okay.
So for task two, we basically next slide, please. We compare the effect of different Ks and different lambda, and we can see that basically when K equals 50, we can reconstruct the phase better. And yes, so here's the...
I had a question about this, right, guys? I told you to put different faces, right? Because if you put all the same faces, there is not much that we can see. Okay. In the final report, please put different faces. Okay, go ahead.
Okay. So here is the compare that only compares case when we fix the lambda.
Do you remember? Go ahead.
And last time, you asked why when K equals 20 and like you think I missed the K equals 10 and K equals 20. And
it was a question. Okay.
Yeah.
I didn't accuse you of anything. Don't make me sound like.
And I think I checked my code and it was correct. And I think it was because like maybe when K equals 10, we took less pictures, and each picture we can show their characteristic more. And when K equals 20, the edge is more blurred because it was like because of the effect of averaging. That's my assumption.
Let me think a second. Because the eigenvalues, they're still ordered from the largest to the smallest, right? It's true that if you add more components, you add more noise. But still the power should be going down, right? So that's why it's surprising. So do you remember what's the name of the data set? You remember what is the name of the data set?
I forgot, but I can check.
Just check, because I want to ask you.
Olivetti.
Oh, okay. Do you know what is Olivetti?
No, the man's name or Olivetti.
So Olivetti was was an early Italian computer company. They used to make typewriters, right? And then they transitioned to computer, and and then the company failed, right? And people said it's one of the great missed opportunity for Italians to to reach the technology, right? Because you can imagine that when computers came out, right, there was a lot of capitalization, right? There was a lot of people that were trying to build hardware computers, right? And so it was a great disappointment for us. So these faces are all Italians, right? That's my point.
Okay.
The other thing is that I think they just picked a lot of engineers, right? And the issue is that, of course, since it was Olivetti, no people of different skin colors. There was not much diversity. No women, right? Because of course, times have changed, but not so much. Okay, let's put it that way. Since you are a woman, maybe you can relate to this. And then a bunch of people with glasses, right? So 50% of the people, they screwed up their eyes. So yeah, just something funny. Yeah, just something funny. Olivetti. Let me just. Okay, go ahead. Yeah, because the headquarters is close to my home. Yeah. I'll just paste it in Slack. You guys take a look and think. It could have been the Italian TSMC, guys. Maybe at that point there would be a Taiwanese professor that comes to Italy to teach instead of an Italian professor that goes to Taiwan. Go ahead, guys. Go ahead, please.
This is not my part. I don't know what.
I think
But still, you still know what
show up
what's
and
going on.
Just like a different bias, and like next with lambda, yes, more lambda, and next page will show the condition number for the different lambda, and show that when lambda is higher, and the condition number will like drop more quickly. Yeah, and next page will show like the arrows thing.
Can you go back one? Can you go back one? So this one you said bias. These are bases, so don't confuse the
bases. Oh yeah. Okay.
And also here, stay there. Jeez, is this class or is just a movie that you want to go so fast? So the thing is that the bases, they are in this case they are not constrained to be positive and negative. Okay, so I want to say this: the pixel of the images are between 0 and 255, right? But the bases that you have here are both positive and negative. So when you see these bases, right, they are the gray color is the 0 entry, and then the white is the positive, and the black is the negative, right? So you see that the different faces they're adding glasses, and they're so for example, right? There are a lot of faces with glasses, right? But you see sometimes glasses are black, sometimes are white, and that's because some bases add glasses and some bases subtract glasses. And then you see that when you subtract a glass, then you also subtract the shadow under the eye that is generated by the glass, right? So the bases are basically, you can imagine that you're superposing multiple of them in order to reconstruct the original image. Okay, go ahead. Because in the next slide, go to the next slide. In the next slide, instead you use this, you use the 0 to 5. That because you're representing the error. Okay, go ahead.
Okay, I can take talk about task 4. It's about NNF, and what is NNF? After we do the Cholesky vectorization, and you do NF to make the all element of the decomposed matrix to be all the element will be not non-negative.
Let me correct a little bit there, right? So in the SVD, right? So think of it this way. In the SVD, we have a set of bases, right? And we express every phase as a linear combination of the bases. And we choose how many bases we have for this reconstruction. So when we do SVD, what we ask is the bases are orthogonal, okay? So if you take the inner product between the two bases, then the inner product is 0. Is that clear?
Not very understand the.
So go back to the go back before. Go back one. Go back one. Stop here. Stop here. Stop here. Stop here. Okay. So what you're doing is this. Somebody gives you an image from the data set, and you're expressing this image as a linear combination of these 100 bases that you have, and these are the bases that you have that you've chosen from SVD. And these bases, they are all orthogonal. Okay, meaning that if you take this image and you vectorize it, and you take the inner product of any of these two images, the inner product is 0. Is that okay?
So if the product will get negative value, you need to do some process make it non-negative.
Stay with me. So when you do the reconstruction with SVD, the constraint that you impose on your basis is that for the basis to be orthogonal. When you do NMF, you throw away orthogonality and you put non-negativity of the basis. Is that understood?
Mm-hmm.
Are you sure?
It's hard.
No, it's not hard. It's not hard. I'll give you an element in the data set. And I'll tell you, you have to express this element in the data set as a linear combination of a certain set of bases. Okay? But then, of course, you can impose something desirable about this basis. Okay? And in SVD, the desirable thing that you ask is for the basis to be orthogonal, so that a certain base does not represent what another base represents. When you do NMF, you ask for the basis to be non-negative. That's it.
We can see the
Yeah, exactly.
the feature is quite straightforward here. Because most part is non-negative, so all part is non-negative. So you don't have minus number to cancel each other. So
Correct.
if you want to construct the main phase, you need to decompose main phase feature to like ice. This is like glasses.
Those are eyebrows, right? That's the color of the eyebrows, right? These are eyebrows.
Yeah. Yeah. Just eye area, and this is nose.
Yeah, and that's a shadow. That's a shadow of the nose, right? Because the light position, it's uniform, right? So you always have the shadow casted by the nose. Yeah. So depending on how big is your nose, of course, this is an Italian problem, right? Depending on how big is your nose, you have more or less shadow under your nose. Go ahead. Then you have the light in the eyes, right? Go ahead. Go ahead.
So this is the basic of your face, and you need to construct a human face with these parts. And we talk about.
Let me just stop you there, right? But the thing is that this factorization makes sense, right? Also from a physical perspective, right? Because imagine that you have an image, and the image is composed of pixels, and pixels they cannot generate light, right? So the pixels are reflecting light. So you're telling me, so it makes sense that when you decompose it, you account for the reflectance of each of the parts of your face. And so this decomposition makes more sense because SVD, you're subtracting components, but in order for subtracting components, you will have that some parts of your face generate light, right? Which is not the physics. So the decomposition makes sense also from a physical perspective, right? Go ahead.
And we we try different K. It's different with the result of different with the result of task 2 because the Cholesky result is pretty much non-negative when K is small, but when K is large, it will be a lot of negative value. So you do an NF with a lot of negative value, so it will destroy the perfection of
of course you don't have orthogonality.
Cholesky result.
So what you're telling me is that when you run the algorithm, right, you don't get any advantage of putting more than 20 bases. Wow, that's interesting. That's interesting.
But you can see this image. This is the previous task 2 result from here.
Yeah.
And you can see when K is great, K become greater, the relative error become lower. But in an NF result, when K become greater, the relative error become greater too.
But this is the question that I have for you, right? Here you see the intersection of two things, okay? One is that the algorithm that you have for finding the basis cannot find some good basis over 20, right? So one aspect there is the algorithm, right? And the other aspect is the nature of the problem. That maybe really, if you want to do this decomposition, then you don't have more than 20 bases. So right now, like in my mind, I don't know where we are, right? I don't know where we are, meaning that if the algorithm was perfect, the performance could not get worse, okay? Because if the algorithm was perfect, then it will give you bases that are all 0, okay? So the result cannot get worse. So right now, I don't, you understand what I mean, right? I don't know how much is the performance constrained by the algorithm that you have, and how much is constrained by the dimension of the problem. It's nice. Okay, go ahead. Tell me something more.
Okay, I try fit K equal to 20 and try different lambda. When lambda is too large, it will affect the original value of the matrix. So it will cause the makes a lot of error. So the relative error will be higher. And in lambda is equal to 10 power of minus 5 is quite well here. When the lambda is small enough, the relative error will be low. But if you take too slow lambda, the lambda sometimes will be ignored when the diagonal value is large. So the NNF algorithm will be fail sometimes because you need to square root the diagonal. So if some number is negative, the square root will be fail. So you can see when the lambda is very small, the curve will be not that smooth. It will have a lot of bounce.
Let me think. It's good. It's nice. Because here you're using ridge regularization in order to bring up the eigenvalues, right? And then this one here leads your Cholesky decomposition. And then from here, you set elements to non-zero. Yeah. Nice, nice.
Okay. Here's the fixed K with lambda. It's pretty much same with the previous result.
But this is with SVD, right? This is with SVD.
Yeah. It's
Because you
not
just told me that you don't need more than 20, right? So this is for SVD, correct?
Yeah.
Are you sure?
Not it's ALS, I think. It's the result of task 2.
Yeah, exactly, right? Yeah, this is SVD. Yeah, it's the same slide. Yeah, this is SVD, right? Go ahead. This is the relative error with SVD.
I
Do you
just
have a
need,
relative error with NMF? Yeah.
I just compare with these two slides with the previous result.
Okay. Good.
It's pretty much for task 4.
Let's see 5. Let's see task 5.
Who is responsible for task 5? Is he there? Is he here?
I believe in you guys.
Hey, hello.
Hello.
Okay, so here we talk about the benchmarking against the SVD. Yeah, yes, next page. And as you can see, according to previous task, NMF error is increasing as K increase. And what we expected is it should decrease as SVD and ALS do. The NMF curve is expected to sit above both SVD and ALS and decrease as well, showing the cause of enforcing non-negativity. Both curves of SVD.
This is the cost. This is the cost of the algorithm, right? This is the cost of the algorithm.
Yes.
Because as I said, the performance cannot increase because otherwise it will just set the additional basis to 0. So if the algorithm was optimal, then there should be a straight line, right? So never decreasing. But the algorithm that you develop using the Cholesky does not enforcing the elements to 0 does not. Can you show me the algorithm somewhere? Do you have the code for this algorithm somewhere? The NMF one? Do you have the code? Can you show me the code a second?
Wait a minute.
I wonder. I thought the performance would be better. I thought the performance would be so terrible. You have to share. We are still seeing the presentation.
We're
still seeing the PPT.
You mean you need to see the code or?
Yeah. Show me the code.
This is the NMF code.
But we are still seeing the PPT presentation. You have to change the sharing.
Oh, how do I?
Jeez, it's only the 4th month of class. Come on. You have to just to share something else, right? You click and there is share something else. Just click that.
How do I?
Maybe you can try close the sharing screen and open it again.
Oh, wait.
Have you been coming to class or what did you forget?
Oh, I share the wrong screen.
Yeah, exactly.
I didn't notice that. I bet.
Okay, let me see the code here. Good. Oh, so that's a solver. Show me the solver there. Okay, so you have the value 16. That's easy, right? That's the easy part. Forward substitution. Okay, go. This is the Cholesky solver. Okay, show me the NMF one. Yeah.
NMF one is
alternating least square. Yeah, that's alternating least square.
Wait. Let me check it. I think it's not here.
Task 4, task 4, task 4, task 4. Keep going down. Is it there?
You mean you see? But
Let me
you
see.
need
Olivetti faces goes down. Cholesky factorization, okay. Cholesky solved GMB. Okay, let me see this one here. So in Chinese, thank you. How do I know how to say Cholesky factorization in Chinese, guys? Okay, W is, so you start with W, this is random. Loss history, go down a little bit. Frobenius norm. Yeah, that's it. That's it. That's it. So your epsilon is 10 to the minus 15. What is your epsilon there? Or you do the clipping? What is the
epsilon. I think it's 10.
10 minus 10. Yeah,
10,
go down a second. Oh, so the performance of this, it's so bad. I mean, so yeah, I mean, the performance of this is so bad. 10 to the minus 10. Well, stay there. Let me think. You know that it's only 6 lines for you, right? But there is a lot of things that is happening there, right?
Yeah.
Then do the clipping, and then you just call that. And then the omega, you update the omega, right? Omega transpose, and then you do the clipping there. So your data matrix is the X matrix, right? Yeah, the X matrix is there. Yeah. Interesting, guys.
Yes. I think
Yeah,
yes.
that's it. Yeah. That's it.
So
Yeah, the
we
rest
can
is okay.
go.
The rest is okay. Yeah, the rest is okay. Okay, go back to the PPT. I'm just wondering. I thought he would do better. Because, for example, right? Yeah, go back to the picture. Go back. Go back to 23. Right. Go back to 23. This one here. Go back one. So here, right? If I were to do that, right? What I would do after, let's say, every 20 basis is that I will fix the initial 20 basis. Then I look at the approximation error, right, after 20 basis and the original one, and then I will apply NMF on the error matrix. Is that okay? You agree? Guys?
Can you say that one more time?
Okay, so look at what happens at 20, okay? What you can do is the following. You fix the first 20 bases, right?
Right.
Then when you have to decide the new basis, what you do is that you consider the error, right, at 20 bases, and you use the next 20 bases to represent the error term of the previous 20 bases. So instead of starting from the original matrix X, right, I will take X minus the approximation that I obtained for the first 20 bases, and I apply NMF on the error matrix. Does it make sense? Guys, does it make sense?
Not very understand.
Why not? Why not? Why not? This is a linear approximation, right? So this is the sum of multiple terms, right? And so you can fix the error at a certain point, and then you can do the composition of the error, right? Okay, go ahead from here. Yeah.
Okay, so both curves of SVD and ALS decrease as K grows, which is expected. More components means better reconstruction. SVD and ALS are nearly indistinguishable on the plot, which visually confirms that well-tuned ridge ALS is competitive with the optimal SVD approximation. SVD and ALS track each other very closely. When lambda is small, ALS essentially converges to the same solution as SVD.
Mhm.
SVD is theoretically optimal, but in ALS, with a well-chosen lambda, achieves nearly identical reconstruction error. The trade-off is that SVD has no interpretable part-based structure, while ALS can produce more meaningful basis images.
Yeah, maybe. Yeah, maybe.
Okay, next page.
That's nice. That's nice. Go ahead.
This top agent faces shows the behavior. The first few shows the global structure, like overall brightness and contrast. From U6, you start seeing more specific features like glasses, mouth, and facial hair. The singular values also drop steadily, confirming that early components carry the most information.
Mm-hmm.
Okay, next page.
I say go back a second. I was looking at the numbers. So the first explained variance is 80%, right? So the second one is 66. Yeah, that's good. You see that there is no trace of a woman. Maybe the U4 looks like a feature of a woman, but yeah, not many women in the data set, and most people with glasses. Yeah. Okay, go ahead. Go ahead, guys.
I think the
Oh yeah, just go ahead. Just go. Next thing. Yeah, so this part we're going like compare the SVD and then
this should be fun. This should be the fun part, right? This should be the fun part. Yeah, that's it.
Yeah, so as we said previous, that SVD produce like a diverse but a bit ghostly face, because it has the negative value, so the digits will be like more sharp like that. So yeah, and the NNF will produce like more realistic but identical face.
Yeah,
so yeah, we look at this SVD first.
Okay.
So yeah, it learns the global features, what we call eigenface, and it operates entirely without boundaries. So it allows for both positive and negative value when we generate a new face by sampling random latent codes. So the model is freely adding the subtracting least global features. So yeah, the output will show like this. And next page, we can see the NNF1 and
much nicer. Right? Look how much nicer it is. Yeah, very nice.
Yeah, the NNF face look like incredibly more real, but almost like the same similar phase, because the answer is that lies its strict boundaries that NNF strictly enforce non-negative, so it only allows the addition of positive phase parts. So, and furthermore, the generate a new phase, we restrict the model to use a convex combination. So yeah, the convex combination force every newly generated phase to like stay securely inside the safe zone. So yeah, safe zone of our training data.
Very nice.
So
That's
because
very
it just
Did you have fun with this task? Did you have fun?
but this
Huh?
task is not my part because that Flip
Still, I mean,
didn't.
you guys should work together, right? I mean,
Yeah.
when I dreamt up this task, I thought it would be fun for you guys to generate some faces, you know,
Oh,
see if they might resemble you, right? Yeah. Very nice, very nice.
Okay, so
Always coming up with excuses. I just asked you if you like the task, right? I didn't ask you. I didn't blame you for anything, right?
Yeah.
Go ahead. It's not my part. It's not
so
my part.
yeah, next page. Next page, I think is a compare. Yeah. So
Who's your favorite guy here? Who's your favorite guy?
Huh?
Who's your favorite face? Which one is your favorite? If you had to pick a friend among these faces, which friend would you pick?
What?
Who would you want to be your friend among these faces?
Maybe the second phase of NNF.
The guy looks
my
friendly,
choice.
right? The guy looks friendly. Yeah.
Look more friendly, I think. Yeah. And yeah, the next page is the conclusion of the survey. Next page. Yeah. So to summarize, is that this illustrate the fundamental manifold dilemma in linear generative models that SVD gives creative freedom to explore the unknown, but the cost of realism. But NNF will, on the other hand, guarantees absolute realism, but traps in the safety of the average. Yeah.
I think for me, when I give you this task, is that I wanted you more to understand a little bit generative AIs, right? So because the tasks that I give you, right, I also try to like choose different machine learning tasks, right? And I think this is the first time that you do some generative AI. Usually you do classification, or you do clustering, or you do regression, but this was a new task, right? So that's why I asked you if you liked it, right? Because you never did any generative AI. So this is your first introduction to generative AI. Go ahead.
Yeah, so I think that's it.
That's it? Okay.
No, we can go to go to
Okay,
test.
go ahead.
Seven,
Let's
yeah.
see what happens. Let's see what happens.
Okay, and I do some optional extensions next. Like 7A is I compare the NF initializations schemes.
Wow.
And I do the random and NNDSBD. And this is a convergence curve. And we can see the random one is and the random one has more error at first, and then but it does well when the iteration number increase.
So just a point here, right? So you will not look at the final error, but you will look at the smallest error, right? So in this table, right, I understand the final error is there, but also the smallest error will be relevant, because when you run the experiment, you can check what is the smallest error after you're done.
The smallest is like the 7th 17th one.
I see. Yes. Yeah, exactly. And so
Yeah.
probably that's also like 0.23 something, right?
Yeah.
It looks just a little bit worse. Yeah. But this is very interesting, right? Very interesting.
Yeah. So and
Yeah, go ahead. I didn't want to interrupt you. Huh?
and next, and these are the faces.
That's a very good point, right? That's a very good
Yeah.
point because the bases are not unique, right? So the fact that if you run the algorithm twice, you obtain the same basis is not going to happen in general, right? So SVD, SVD, if you run the algorithm multiple times, the solutions are still aligned.
Yeah.
But with NMF, you don't have any guarantee about the experiment being reproducible in that sense. Go ahead.
Okay. Next one.
No, let me go ahead. Stay there. Sorry. Go ahead and let me think. Wow, very interesting. So is there any component that aligns? Not really, right?
I think these two are totally different.
Right. It seems so. You can see, right. So there is the, let's say, left and right, right. So you see that in the third row there is the. Oh gosh. Wait. Let me think a second. So because I thought there is the shadow under the nose in both data sets, right? And then there is the shadow under the lips, but the light around the eyes. Okay, so the light around the eyes, it's the one that is most similar, right? Third row on the left, second row on the right. That's the most similar. Then the lips, nothing. Oh, so interesting. So that's a good point. Nice. Okay, go ahead. It's really nice.
Okay, next one. And then it's a 7B. I compare the divergence-based multiplicative update NMF. And I do the KL and NIS.
Okay. Go ahead.
And these are the divergence plot.
Do you have the results of the approximation for this as well?
Yeah, and it's in the next page. Okay.
Let's see.
Okay. Yeah. The plot is like IS and KL are very close. And
Question. Let me ask you. So I wanted to see this across multiple dimensions. This is for k equal to 20 only, right?
yes.
I wanted to see it for different k's, right? Because, can you go back one slide? So this update rule here, right? You see how it's different from the update rule that we just saw using the Cholesky factorization, okay? So in my mind, this update rule, it's more performs better than the one based on the Cholesky factorization that we saw before. So I wanted to see if this approach will give you a better NMF approximation for as a function of k, right?
Okay.
Do you know if that's what happens? Do you have a plot like this?
Yes, I do it on the 7C.
Okay, go ahead. Show me.
Okay. And you can next is the pictures. Like these two are very same.
Exactly.
Yeah.
Exactly. It's a better update. Yeah. It's very good.
Next. And
Okay, very nice. Okay, go ahead. Tell me about this.
yes, and in 7.3 I examine whether the low dimensional representations preserve enough identifier related information. And I use the five-folded cross validation to compare the classification accuracy.
So what do you do here for classification? Because you have, how many classes do you have? You have two classes, glasses and no glasses, right? No, which classification is this? Should be
And
glasses, right?
I do you can check the code. Right.
Yeah, go ahead.
Mm.
Because it's 40 people, but if you're doing classification, you're not classifying people. I think you're classifying over glasses and glasses. Let's see. Let's check. Yeah, we can look at the code. No problem.
I can turn to the code.
Wait a minute.
Let's look at the code. Let's see. Either you do logistic regression over glasses, no glasses, because I don't think that you do, or you do a deep neural network. Okay. Let's see.
7C.
Okay, stay there. Don't start scrolling. Let me see the beginning. Yeah. So when you logistic regression, okay, logistic regression over what? Go down a little bit. Let's see. Five-fold cross validation. Very good. Go down. Where is the Y label? There. Let me see. Stay there. Don't move. But the labels loaded earlier. What are the labels that you use? Where do you find the labels? Check the labels. Let's see which label you use. I think the labels are loaded in task 7. Try to go to task 7.
Yes. It's in a setup.
Yeah. Go down. Labels. But where is the label? Y test. Can you check the Y label? Should be privative faces. Y label. Yeah, it should be. Yeah, it should be. Let me check. I check a second there. You guys check your code. I'll check on Kaggle. What is the Y faces?
Wait a minute.
Let's see. Oh.
This one? Oh shit.
Don't swear. We're being recorded. Yeah, just I'm checking the internet. You guys tell me when you figure out what is
This
it.
one?
I'm checking load. Let me see.
I don't know.
No. This is the label for the plot, right? This is the Y label for the plot. I want to know what he's classifying, right? The classification. I want to know the classification. Can you tell me how many? Again, these are the label for the image. I want to know what is the column of Y label. If it's 0 glasses, 1 no glasses, or if it's one of the individuals, right? Because you're doing logistic regression, which means that you only have 2 labels. And I just want to know which label you're taking.
I'm finding.
It's your code, you guys. I understand you guys automate everything, right? But,
Go to the setup.
Okay.
And down there. Yes.
This one?
Yeah. Good.
So is it the subject ID or because if you load it like this, it's the subject. Again, this is an image, right? Here you're just plotting an image. Okay, no, that's the. I think it's the. Can you just 040? Yeah. So your labels X. Because if it's your labels are of support 40, then it's the identity of the individual. But then how can you do? You do logistic regression over the 40 individuals? Okay. I think that's the. Yeah.
we can go back to
Does
the.
anybody know how many labels you have? If it's 40 labels, can you print it out quickly? Just to... Yeah, just print out the Y labels. If we see that it's 0, 1, if it's or it's number between 0 and 40. Can you print it out?
The operating. Error. I don't know why.
Yeah, you have to run the task 0 first. It's written there, right? Run task 0 first.
I think it will take time.
I think it's gonna be you're doing logistic regression over the 40 individuals. So yeah, because I if I wanted to see what is the relative, what is the like what do we compare the performance of? Yeah, because there are 10 different images for 40 individuals, right? So I want to understand what is your error rate.
Yeah.
Okay, let's go back to the slide and then you tell me what is the result. Once it's done. Yeah. Okay, let me see again the error rate. So the error rate. Oh, okay. Oh, wait. Classification accuracy. So because got it. So you start from 40%.
Yes. And I first do this only like 150 and 25 and 10. And I noticed that there's a big increase in between 10 to 25. So I do more points and there. And I think when the K is very low, when K is low, when K is low, the accuracy is very low, but it increased very fast. And when it reached 20, it's almost like no change from K from 20 to 100.
But this is also what we saw, before, right? That
Yeah.
if you get the first 20 bases, then you can represent faces very well.
Yes.
Very nice. Go ahead.
I think that's all.
That's it?
Yeah. I didn't do a 7D.
What was it? What was the 70? What was the 70?
It asks us to like compare between the faces and others, like writing.
Yeah, MNIST. Yeah, you could compare the performance with MNIST. Just to understand what is the difference in dimensions. Yeah.
Yeah.
Oh, good. Okay, very nice, very nice. Yeah, the initialization one was nice, and the update rule with the KL divergence was also nice. Okay, very good, very good. Okay. Let's see if we can figure out if it's really the 40 dimension. I think I'm getting more and more getting more convinced that it's the 40 dimensions. So guys, tell me what you want to do. We can go to the challenge 4, or we can do discuss more about the final. I can give you some background on the final challenge and orthogonal polynomials. What do you guys want me to? Let me ask. Do you guys want me to go to the challenge or move to the? Should we go through the challenge together? 0/1 question mark. 0 equal yes, 1 equal no. Okay, let me see. Okay. Hey guys. Oh. You let me know if you get to the 40 labels. Huh? Yeah, because understanding that you do logistic regression, you really can tell 40 people apart from 10 images. It's pretty powerful, right? So in the deep learning, performance will be much will require much larger data set for sure. But again, the illumination is very uniform. The problem is very simple. So I wonder. Hope. So I'm gonna make the case for you here. You should embrace. All right, guys, you should embrace challenge 4 because challenge 4 is very cool. Okay. So we're back with our fashion analyst. So nothing to discuss there. But the topic is sketching. Okay, what is sketching? Sketching means that when you want to do some linear algebra operation, right, on matrices, instead of doing it on the original matrix, what you do is that you hit the matrix with a smaller matrix, right, so that you obtain a sketch of the original matrix, or a smaller version of the original matrix. You perform your linear algebra operation on this sketched matrix, and the results that you obtain are comparable to the original operation you were going to do. And this is incredibly useful, right, when you are only interested in obtaining an approximate solution and you want to speed up computation. Okay, so for all this SVD problem that we saw, PCA type of application, it's clear that we do not need to have the exact solution. So even if we had some approximation of the directions, that will be good enough for us, because sometimes we are interested in an algorithm that has a very high throughput, and the precision is not so crucial. Okay, so let's say that you're doing this PCA for clustering. Okay, and you know that you're going to perform a 10% error on the cluster anyway. So what is the point of spending a lot of computational resources trying to obtain the perfect SVD, right, when then you're going to be hit with a 10% error anyway? Okay, so you might as well cut down on the computation as much as you can, because the error that you have is still going to be significant. Okay, so what is the idea here? You have a certain matrix that would, let's say, which is n times d. Okay, n is the size of your data set, as we usually do, and d is the dimension of the data set. Okay, now you hit this object with an m times n random matrix. Okay, random matrix. The keyword here is random, and you produce this matrix A tilde, which is equal to your sketch times your original matrix. Okay, so we all know how the word works, right? So we start with n times d, we multiply by m times n, so the matrix that we obtain is m times d. Okay, so imagine that your original n was 10,000 and your m is 100. Okay, so you have a reduction of 10 to the power 3 on your on the size of the matrix that you're handling. And how do we check your how do we construct this sketching matrix? Well, we can have entries at random. Okay, this is where the beauty comes in. Okay, the entries are fully random. One, we just take them to be a Gaussian random variable with mean 0 and variance 1 over n. And the other one, we choose them uniformly at random between -1 and +1, divided by square root of m. Okay. And then what do we do? Instead of computing the exact product, A times B transpose, right, what we do is that we compute A tilde times B tilde transpose. Okay, so again, A times B transpose will be a matrix n times D times D times n. So the matrix is an n times n matrix, right? So it's a massive matrix. But here we approximate it with a matrix which is D times D, right? But it's obtained as D times M times M times D. So it's a much smaller matrix. And then what we do is that we look at the difference between the original A times B transpose product and the approximated product using the sketching matrix. And as the M changes, right, you will see that the error decreases very, very quickly. Okay, so incredibly enough, if you take a matrix and you hit the matrix with a matrix which is sufficiently random, and you use this to approximate a matrix product, you can approximate. You can have a very good approximation error of the result C. Okay, and as usual, when we talk about matrices and we have errors, we have to decide how we're going to measure the errors, and we will take the induced L2 norms and the Frobenius norm. Okay, so now if I ask you if you believe in this, you guys should be very, very skeptical. Okay, you guys should have some inherent skepticism with respect to the performance of this, because of course there is, it is very strange. It's a very strange thing, right? That we approximate the operations with this random sketching. Okay, but indeed this works, and you can do a plot, and you can see that it works very well. Then we go ahead and we approximate not only matrix multiplication, but we use this to approximate pseudo inverses, right? So now we take a sketch of the matrix. So we have the matrix A, which is a positive semi-definite, and we have a Q sigma Q transpose. Okay, so this is again this is your eigenvalue. This is your eigenvector matrix. This is the eigenvalues. And now we try to approximate this we try to approximate the pseudo inverse using sketching, right? So instead of taking A, we take we want to solve AX times B, and instead of solving AX times B, we solve S times A multiplied by X is equal to S times B. So we sketch the matrix A. We find the solution X in this much smaller space, which we call X tilde, and then we see what is the error in X, in between the original X and the approximated X tilde. Okay, so before we were doing matrix multiplication, now we are solving least squares, right? And we're using the pseudo inverse to solve this. And incredibly enough, this also gives a very good approximation of this. So now, if you believe me that you approximate the matrix multiplication, and you believe me that you approximate the pseudo inverse, then it's natural, right, that we also try to approximate SVD. So same stuff. We construct our sketching matrix S. Then we decompose the much smaller sketch matrix, and then we go ahead and we find the SVD dimensions from this, and then we can compare the frequent direction on the original matrix and the sketch matrix. Incredible. Okay, and then you do this same procedure that we did before when we were doing, for example, fashion MNIST, right? You can do classification, and you can do PCA and so on and so forth. But instead of doing it on the original problem, you can do it on the much smaller problem, and then you have the usual questions, and then you have the usual derivatives. Okay. So this one here, I made it a little bit lighter, meaning that I didn't put so many details because I want you guys to start working on the final project. So in my mind, if you can start working on this challenge now, then you'll have more time for the final challenge. And then as we move to the final challenge, then I will keep presenting the material from the on polynomial approximation, orthogonal polynomials, and something like this. So this will be relevant for your final challenge. But of course, I know that you guys will not work on the final challenge until 2 days before the final presentation. And then we will ask Nafal to give us a date in which you guys want to see. You guys think I don't know you, but I still know how you guys operate after 10 years of doing this job. And then we can all discuss the final challenge. Also, the final challenge is very cool, guys. I hope you will appreciate the final challenge because I also think it's a very, very cool idea. Okay, so as I said, sketching it's a very beautiful topic, and I worked on it for research for a certain amount of time. And there is this beautiful class in Stanford on the sketching, which matrix sketching. Matrix sketching methods. Yeah, let me post here. Something. So this is the class from Mert Bilanci. Yeah. I'll just post the PPT presentation in Slack. is very nice. So, yeah, doesn't matter, but I was co-supervising a student that was working on this topic in Stanford. And so yeah, so try to sketching it's very, very interesting, right? So and it's somewhat unused by people simply because it's not a very well known and very well established numerical method yet, right? So for example, there is no hardware for matrix sketching, for example, when you do backpropagation for deep neural networks. Okay, so what me and my student investigated was sketching for backpropagation. Okay, so we haven't done this in this course, but it's something that you guys should study soon. So when you train a deep neural network, you do the forward pass, and in the backward pass you have a lot of matrix multiplications that you do in order to update the weights between one layer and the other layer. And since you're doing backpropagation, you are doing this operation not on the full data set, but only on the batch, right? Only on the small amount of data. So the result of the operation is going to be already very noisy, right? And it's going to be already an approximation of your optimal backpropagation rule. And so if you do sketching on this backpropagation, you introduce some noise on the computation of the weights updates, but the noise is already present because you only use a subset of the data to compute the gradient and not the full data. And so the error that you introduce with sketching is below the error that you introduce by batching the data. And so it is very reasonable, it's acceleration using sketching of this backpropagation will be something very effective. And we show that with a couple of nice rules, you can really approximate backpropagation very effectively. But I think, it's still not established as a hardware acceleration, for example, right? So if you buy an NVIDIA chip or an NVIDIA card, they are not going to do sketching. But the results are, mathematically, the results are very well established. And again, it was one of the more recent numerical recipes that were discovered maybe 15, 20 years ago. And it revolutionized, introduced a lot of new research topics and new research directions. And it's very interesting, yeah. Because, from your perspective as students, maybe you think that when you study some maths, it's always math from the 1600, from the 1800s. There is nothing new that happens in mathematics or in terms of algorithms in the last 200 years. But in actuality, there are always some interesting development of research also on basic mathematics and numerical methods that some of you don't know about because you're still catching up with what is happening in these days. Okay, very good. Any questions? Otherwise, I'll just show you what we're gonna cover next very briefly, and I'll let you guys go. Here, it should be this one here. Okay, so we're gonna cover in the next slides. We're gonna cover to this NYU set of slides. Okay, so NYU, our friends at NYU, and we're gonna cover more functional analysis. So we're gonna say, oh, there is a function between 0 and 1. You can represent it with a polynomial, and so the projection that you have seen on the Gram-Schmidt procedure, right, on orthogonal basis. Now we're going to see it in a functional space, right? So now instead of having a basis over a space, we're going to have a functional basis, right? We're going to have basis function and not basis vectors. And when we have instead of having the approximation of the space, right, of the space induced by a matrix, we're going to have the approximation of a certain function, and the least square approximation will not be of a vector, but it will be of a function. And now you're going to see the idea of a projection on a functional space, right? So then so that what you guys see now is this one here, right? So when you approximate a certain vector over a matrix of eigenvectors, now you're going to see it as an approximation of a function in y and x. Okay, and then from here we're going to go to the Fourier transform, which you guys saw briefly as an introductory topic, but we're going to see it more as in the functional space. And then we're going to give you the final project. Again, for the final project, you should have about a month. Can somebody remind me when is midterm week? Midterm week should be at the end of May, right? Can somebody remind me? I have a terrible memory. Midterm week should be the last week of May, right? So, because I think the last week. Yeah, go ahead.
There's no. The final week is on the second week of June.
Okay, second week of June. Okay. So if I give you the final presentation now, then you're going to have 1 month before your final week. And then I think maybe we can do the presentation a couple of weeks after, right? So you can have a little bit more time. Because I assume that you guys will stop working, let's say 1 or 2 weeks before the final week, unfortunately. And so I can give you a little bit more time to present the solution. I just want to convey to you guys that it's, I mean, it's like learning is more effective when you have a constant speed, right? And you are always working on something constantly. So the idea that you have these final weeks and you have these bouts in which you study 16 hours a day, and then after the exams, then you flatten to zero, then you forget everything. It's a little bit suboptimal. So yeah, I will not want you guys to do the same for my course, because already it's hard for you guys to retain information since you see so much different information in different classes. So yeah, let's try to figure out something that allows you to work with a little bit of peace of mind on the final project so that you can actually remember something of what you did with me. But okay, so challenge 4 is released now, right? So in 2 weeks you'll present it, and then after 2 weeks you will have the final week. Maybe 2 weeks after we do the presentation of the final project. Okay, so if I release the final project at the end of this week, you will have 1 month and a half to work on it. It's understood that you're also doing challenge 4, so that will take 2 weeks away from that, and then you will have a full month to work on it. I think it's a fairly reasonable deal. Okay, guys. Okay, I'll stop the recording now. If you have any questions, you guys let me know.